Hello everyone. This week we are going to first continue with our thermal energy notes from last day. So we're going to do two example questions so that you can actually finish the worksheet 7.8, the two questions that we didn't do last time. All right. So to begin with, we're going to look at conservation of energy, conservation of heat in this case. So when you have one object transferring energy from itself to another, all the energy transfer should be conserved. That means in an ideal situation, the energy lost by the first object should be equal to the energy gained by the other one. So let's say you're touching a cup of hot tea, then the energy lost by the cup of tea, so the energy lost by one substance, the cup of tea, should equal to the amount of heat energy gained by you. So the energy is either in the cup or transferred to you, right? So there's no way that the energy could just be evaporating. Now that's in ideal situation. That's assuming that both you and the object have really good thermal contact and you're not losing energy to the environment. So therefore, we can then come up with this rule, which says that if you take the energy loss from one object and you sum it with the energy gain from another object, then the total of this calculation should be 0. Now, so the object that's losing energy has a negative sign. The object that's gaining energy gains positive energy. And since the amount should be the same, if you subtract them, the answer should be 0, right? So if you add them, sorry. Now, so for example, what happens when you have, so let's look at one example when you actually drop something really hot into something that's colder. So for example, I have a very small block of lead in this example, 0.5 gram of lead at 100 degrees Celsius, so really hot. And then I want to cool it down. Now, one of the reasons why people use water to cool down a lot of things is because, so for example, right, firefighters use water to put out fires. So why? Because water can absorb a lot of heat. So for example, I have a block of lead that's really, really hot, and I dump it into water at almost room temperature, 20 degrees Celsius, right? So what is the final temperature of the mixture? Now, what does that mean? So we look at this situation like this. So this is a piece of lead, and it is very hot right now. So it's a 100 degrees Celsius piece of lead. So it's really hot. And then we have a bucket of water. So the bucket of water below it. So this is just 20 degrees Celsius at this point, and it's water, right? Okay, so now what happened is if you put the piece of lead in there, then you're going to, and then you wait a while, of course, right? So let's say you drop the piece of lead inside. So now they're like this, and you wait. So you drop it in, and you wait. So you wait for a long time. Then what happened is eventually, you know that by logic, and you have seen it in everyday life, that the water and the lead is actually at the same temperature, right? So they have a different starting temperature. The lead starts at 100, the water starts at 20 degrees Celsius. But they should have the final temperature exactly the same, right? When you put anything hot in contact with something that's colder, eventually those two objects reach the same temperature. Now, what temperature they reach? Is it like exactly in the middle? For example, in this case, like maybe they meet somewhere at like 60 degrees Celsius? I don't know. But they will meet at some temperature. So what we want to do is to find out what is their final temperature. What is this mixture's final temperature when it's all cooled down and done, right? So we're going to use that concept that we just talked about earlier. So the heat energy lost from one object should be equal to the heat energy gained by the other. So remember, the first one is heat energy loss, which is from the lead, right? The lead is losing energy. It's the one that's hotter. And water is gaining that energy, right? But remember, from last week, different material gain and loses energy at different rate, right? Water takes ridiculous amount of energy to actually heat up, and lead is easy to heat up. So we will see, most likely, our prediction would be, we will see lead losing a lot of energy and losing a lot of temperature in this case, and water gaining that energy but only rising in like a little bit of its temperature. So 100 degrees Celsius initial temperature of the lead And the final temperature, we don't know. For water, initial temperature is 20 degrees Celsius, final temperature is we don't know. But what we do know is these two are equal, right? The final temperature for both of them should be exactly the same. We just don't know what that temperature is. Okay, so let's continue. Now, so what is the heat energy equation from last day? Well, heat energy is equal to mc delta T, right? So last time we say we discover or we talk about one equation, which is mc delta T. Now for the first one, we're going to use lead. So mass of lead, specifically for lead, change in temperature for lead, right? So this is the heat energy loss. So that's the heat energy loss for lead. Now, if we add it, so now we're going to add it to the heat energy gain of water, which is mass of water times specific heat of water. Remember these numbers, right? The specific heat number is something that you have to go to your formula sheet, that table, to actually find. And then the change in temperature of water. So change in temperature of water, right? Now, so if we add these two, the answer should equal to 0. Okay, I'll just go ahead and pull out these numbers. So for example, mass of lead is 5 gram right here, so 0.05 kilogram. And the specific heat capacity for lead is from, well, last page, right? So it's from the formula sheet. So we look at lead right here. So let's erase all of these. Lead is right here. So 128 joules per kilogram per degree Celsius. Okay, so now we know that. So it's 128. So put 128 in here. So that's from the table. And then the change in temperature. So how much is the temperature change? Well, in physics, change in anything is final minus initial. So it's going to be T final minus, well, I know the initial is 100, right? 100 degrees Celsius is the initial. So there. So this is the lead part. So now water. Water, I have 2 kilograms of water. The specific capacity for water is 4,186. I don't have to look up this number because water is used in almost every question. So I have it memorized. If you want to double check it, of course you can. Now, and then T final, I don't know the final temperature of water. I know it's something, less than 100, right? I mean, think about it. What would be the final temperature? It should be somewhere between 20 and 100, right? Because the lead is going to lose temperature and water is going to gain temperature. So somewhere in between, they meet, but not exactly in between, right? Not exactly in between. Unless you have two materials that are exactly the same, then it will be exactly in between. So 20 degrees Celsius is the initial temperature. So change in temperature means final minus initial, right? Always. Now, and then it's supposed to equal to 0. Now, this you have to use a calculator. So what you would do in this case is take this whole number, right? And then you use a calculator to multiply it, which equal to 6.4. And then you take that 6.4 and you do what? You multiply into this term and this term. Okay, you distribute it inside the bracket. So now let me show you what happened if you do that. So if you do that, you're going to get 6.4, right? Because I have a calculator, so I did it already. Minus. So what's 6.4 times 100? Well, 640. So you're going to get something like this for your first term. Okay, so this whole thing is now this. Got it? Okay, so now I would do the same thing with the second part and allow me to save some time and just write down the answer. So we're going to have 8,372 when you multiply those together. T final minus 1,600. So this is actually a big number. There you go. So 640. Now, so at this point, you have to do some algebra. We have two T final term in here. So what I want you to do is to leave those T final term together on one side and move everything else on the other side. So these two stay on the left. Move the 640 and move the 640 and that negative thing, move it to the other side, right? So do that. Now, do that. And then a little bit of algebra later, you divide both sides by the same number. You get T final by 20.06 degrees Celsius. So, look at this value, right? So the lead, that means what? That means in terms of water, right? The water initial temperature was at 20 degrees Celsius, right? So in terms of water, the water increases temperature from 20 to this value. But in terms of lead, it drops temperature from 100 degrees Celsius to this value. So the water only gains 0.06 degrees Celsius in this whole process, but the lead has dropped from 100 to 20.06 degrees Celsius. So that's why water is used to cool down things. Like that's why the firefighter use water. Because let's say you have a house on fire or anything on fire, you put water on it. Well, water can absorb a lot of heat before its temperature actually increase, right? So if you use water and you dump water into something that's really hot, the final mixture, the temperature of the final mixture won't be high, right? It won't be too high. So that's why water has this advantage. It can absorb a lot of heat. Okay, now, next example is going to be almost the same thing, but with a makeup material. So this one, 0.5 kilogram of a mysterious material called chromium. So I just make that up. That's not a element. Don't try to find it on a periodic table. Chromium. So chromium, at 100 degrees Celsius is placed in 0.2 kilogram water at 20 degrees Celsius. The final temperature of the system is 25 degrees Celsius. Find the specific heat capacity of chromium. That means I make up a material and I term it chromium after myself. And I would like you to find the specific heat capacity of this mysterious material, which means I want to know C, right? I want to know the specific heat capacity of chromium. Now, so I don't know that, but I do know everything else. So I know that, I have a bucket of water, which is 0.2 kilogram at 20 degrees Celsius. And I know that I have a piece of metal, which is called chromium. So this is me, this is the water. And I know that right now, the temperature of that is 100 degrees Celsius. So I drop that in, and I wait a while, and then everything goes to the same temperature, 25 degrees Celsius. Okay, so what is the specific heat capacity? So now the 25 degrees Celsius is going to be your T final. Right, so 25 degrees Celsius is going to be your T final. So we actually do know the T final in this case, which makes it easy. Okay, so we're going to use the same strategy, which is the energy loss. Now, energy loss by what? So energy loss should be, so the heat energy loss should be due to the chromium, and the energy gain should be due to water, right? Because you have water absorbing energy. Now, it's not always like that. I mean, you can have hot water mixed in with cold apple juice, then the hot water loses energy, apple juice gains energy in that case, right? So it's not always water is gaining energy. But in this case, I mean, whoever has a lower temperature is gaining energy. Okay, so now, same idea. So mass of chromium, specific heat, change in temperature of chromium. So that's for chromium, plus mass of water, MC, C of water, delta T of water is equal to 0. So the mass of the metal, how much? 0.5 kilogram. So we use 0.5 kilogram of chromium. I don't know the specific heat, so this is the unknown. So let me just write in red. I don't know that number. I know the final and initial temperature. Now the final temperature is 25 degrees Celsius. The initial temperature is 100 degrees Celsius. So that's my change in temperature. Remember, change in anything in physics is always final minus initial. Okay, so final minus initial. Now, oops, not a equal sign. And then I add mass, which is another one. And that is going to be, so this case, the water is 0.2 kilogram again. And water specific heat, at this number I remember, 4,186. So water is used quite frequently, so a lot of people memorize it. 25 degrees Celsius minus, initially it was 20 degrees Celsius, equal to 0. Okay, so remember in this equation, everything is equal to 0. Now, so in this case, you don't distribute because you actually do have most of the numbers. So just get all of that, and multiply it by c. So in this case, whatever you get left, so you can try this calculation, and then what you want to do is multiply all of these together. You get like a single number, and then you move that number over here to the other side, and on the left hand side you're gonna have some number happy face multiplied by c. On the right hand side you're gonna have a number right here, some happy face, like that, right? And then you divide both sides by the yellow happy face, and you should be able to get the specific heat. So the specific heat, according to my calculation, is going to be 111.6 joules per kilogram per degree Celsius. So remember, that's the unit for specific heat capacity, joules per kilogram degree Celsius. Okay, so now at this point, sorry about that. At this point, the worksheet that you were doing last week, 7.8, you can then finish it up. I think we did 1, 2, and 4. So now question number 3 and 5 can be done. Okay, so now watch the next video for the second part, which is going to be down there. But I'm going to pause it right now because it's a natural way to stop. Okay, so see you in a bit.